Good day and welcome to this webinar about Sensilo's Wat-IF model. I would like to welcome our guest speakers for today, Dr. Leo Carswell and Roozbeh Aminian. We start the webinar with a brief introduction about Sensilo, done by Dr. Corina Carpentier. After the introduction, Roozbeh Aminian will start with his first part about the Wat-IF model. Then we will go to Dr. Leo Carswell, who will present one of the scenarios. Directly after his presentation, we have time for questions to Dr. Leo Carswell. When we have finished the questions, Roozbeh Aminian will take us through the second part of his presentation. And at the end, he will answer all the questions. If you have a question during the webinar, please type your question in the question box in the GoToWebinar control panel, or send your question to support@sensilo.app. And now I would like to invite Dr. Corina Carpentier for the introduction of today's webinar. Thank you.
Thank you very much, Rudolf. Hello, everybody, and thank you for joining us today. My name is Corina Carpentier, and I'm the Managing Director of Sensilo. I've worked in the field of water quality monitoring for over 25 years. Before we dive into the development of the Wat-IF tool, I would like to highlight briefly why this tool fits so well with the objectives of the Sensilo sensor platform. With all our activities, we try to inspire water professionals to continuously look for ways to optimize treatment processes with the help of sensor technologies in order to make utilities more robust and sustainable for the future. We connect water experts from all over the globe to exchange knowledge and develop the best practices in order to foster the use of sensor technologies in the water industry. We keep track of the many rapid developments in the digital transformation of the water industry and thus accelerate the uptake of innovative technologies and monitoring strategies by collecting all available knowledge on this subject and converting it into accessible, readily available information. And there is a lot to digest. So far, we have conducted over 200 interviews with water and wastewater utilities and to ask them about their experience with sensor technologies in the field. We've worked our way through hundreds of research and testing reports and keep track of the latest research and developments through grant programs, peer-reviewed publications, and PhD theses. In addition, we regularly conduct interviews with technology suppliers to find out about new technologies entering the market. Next, we convert all this information into various products, such as our sensor database, webinars, podcasts, workshops, calculation tools, and soon also e-learning modules. All our products have one thing in common. They are designed to provide you with the best possible information in as little time as possible, only a few clicks away. And today we discuss our Wat-IF calculation tool. This tool aims to translate the results of pilot tests to individual wastewater treatment plants. Results obtained at one treatment plant are not always easily converted to another, as the successful implementation of monitoring and treatment technologies is often dependent on the local conditions and the layout of the plant. Wat-IF helps to determine the potential gains and benefits when implementing the pilot technology at your own wastewater treatment plant. The outcomes of the tool support the development of a business case for the implementation of innovative treatment technologies and new monitoring concepts based on the latest available knowledge and insights. Wastewater treatment plants are increasingly required to address the removal of various types of micropollutants, such as pharmaceuticals and pesticides, to improve the quality of the receiving waters and to increase the possibilities for water reuse. However, implementing additional treatment steps to this end requires considerable investments and often increases operational costs, not least because of an increased energy consumption. With water rates already under significant strain and increasing pressure from society to reduce the overall carbon footprint of the water sector to help combat climate change, water utilities have little space to maneuver and need to be creative in order to meet all demands. The Wat-IF tool aims to support water managers facing these challenges. So, without further ado, I suggest we move on quickly to the first part of Roozbeh's presentation on the development of the Wat-IF tool.
Thanks to Dr. Corinne Carpentier for her presentation, for her nice presentation and introduction for Wat-IF model. Hello, everybody. My name is Roozbeh Aminian. I have Master of Science in Chemical Engineering, Separation Processes. I'm a Master student in Water Management at University of Twente in the Netherlands. Currently, I'm researching that Sensilo. I'm working on my thesis, master thesis. I'm trying to combine my engineering and management knowledge by developing a decision support tool, of course, by the cooperation of Dr. Corinne Carpentier. Wat-IF, Water Utility Impact Forecast, a decision support tool for water managers at wastewater treatment plants. This tool is going to help to water managers at wastewater treatment plants in terms of making a decision to implement technologies, new technologies, and monitoring concepts by considering costs, carbon footprint, and water quality. As you can see in the overview of our model, Wat-IF is comprised of 3 main blocks and 2 databases. Block A is about the default settings of wastewater treatment plants. Of course, it's for Dutch wastewater treatment plants because we are working on wastewater treatment plants in the Netherlands. However, it can be easily converted into any other version for any other country. And the second, and also WAVES database, which was used to build the default setting for wastewater treatment plants in the Netherlands. We use the realistic data and information of WAVES database. The second block is block B, is wastewater treatment technologies and monitoring concepts. Those are the input block for our model, for Wat-IF model. And block C is about calculated impact of block B, calculated impact of implemented technologies and monitoring concepts in terms of costs, carbon footprints, and water quality. And it's very important to note that this block uses IronMath database in order to calculate the carbon footprint of implemented technologies and monitoring concepts. Firstly, I'm going to start with the first block, block A, default setting of wastewater treatment plants. Default settings of Dutch wastewater treatment plants. First of all, why default settings? In order to run the model, we need the exact information on the wastewater treatment plant to run the model. However, it is not always possible to use exact information for wastewater treatment plants, so we can use our default settings in order to run the model. But it is very important to note that realistic data need to be entered into the model to run the model and get the meaningful outcome of the model. That's why we used realistic information and data of WAVES database, which I'm going to elaborate on it, to build default settings. But what are default settings? Default settings were built based on the main characteristic of wastewater treatment plants, the characteristics which define wastewater treatment processes, and the characteristics which are going to be changed by the implementation of new technologies and monitoring concepts. Those characteristics are water quality parameters, water quality, size, wastewater treatment steps, and also energy consumption and costs associated with size and wastewater treatment step. We considered nitrogen, phosphorus, COD, and BOD for parameters in terms of water quality. However, there is a wide range of micropollutants to be considered, but it's quite impossible or it's very difficult to measure all individual parameters in terms of micropollutants. And I would say nitrogen and phosphorus are very important because of eutrophication and toxic effects of them on ecosystem. And I would say COD and BOD are highly important because they are used to design the kinetic biological processes and also simulate the wastewater treatment processes. For example, BOD is used to determine the size of a trickling filter, and it is also used to determine the size of activated dislodge unit. Size, in this research, we considered the volume of effluent to each wastewater treatment plant as the size. Size is important because energy consumption and cost are highly dependent on size. For example, when you increase size, effluent to each wastewater treatment plant, energy consumption per cubic meter decreases. When energy consumption decreases, costs are going to be decreased automatically because costs are highly dependent on energy consumption. Wastewater treatment steps are important as energy consumption and costs are highly dependent on wastewater treatment steps. As an illustration, more than 70% of energy consumption is related to biological treatment process. So if we can reduce energy consumption in this step, you can reduce your costs incredibly. And also default values for energy consumption and costs per cubic meter are associated with size and wastewater treatment steps. Derive the default settings of Dutch wastewater treatment plants in the first table. As you can see, nitrogen, phosphorus, COD, and BOD for effluent and removal efficiency rate for those parameters determined. And in the second table, you can see the default value for size, volume of effluent, and also corresponding cost and energy consumption to this size and wastewater treatment steps. In the third table, we considered the most commonly used wastewater treatment steps by wastewater treatment plants in the Netherlands. For example, out of 331 wastewater treatment plants in the Netherlands, 324 use physical purification, lattice removal, 250 use biological removal, phosphorus and nitrogen in main current bypass circuit, and the 147 wastewater treatment plants, Dutch wastewater treatment plants, use chemical phosphorus removal dosage in activated sludge tank for phosphate removal. So these are the default settings of Dutch wastewater treatment plants, which can be used to run the model if we don't have exact information on wastewater treatment plants. But these default settings have been built based on WAVES database. WAVES database is a huge database containing different kinds of information and data. As you can see on the left side of the picture, different data, operational information, financial, energy, in terms of purification management, flood defenses, dredging, and etc. Fortunately, those information are available for each wastewater treatment plant in the Netherlands. As you can see in the right side of picture, COD, BOD, effluent, nitrogen, phosphorus, costs, energy consumption per cubic meter, everything regarding wastewater treatment plants are available, which can be used for building default settings for wastewater treatment plants. I talked about the first block, which was the default setting and also WAVES database, which was used to determine the default setting of wastewater treatment plants in the Netherlands. The second block is wastewater treatment technologies and monitoring concept. There are a lot of treatment technologies and monitoring concepts, but STOWA, which is a research institute in the Netherlands, is quite well known. They have been trying to develop and implement the best treatment technologies and monitoring concept, specifically in terms of micropollutant removal. They have been carrying out a lot of research. They came to conclusion in the report 2018. The most promising wastewater technologies for micropollutants removal are PACAS, powdered activated carbon and activated sludge, ozone oxidation with sand filtration, GAC, granule activated carbon, and UV hydrogen peroxide oxidation. We analyzed those technologies, we studied about them. We conducted interviews with the expert involved in the implementation of these technologies at Dutch wastewater treatment plants. We came to the conclusion the best technology out of 4 technologies is PACAS. Powdered activated carbon goes into activated sludge system. Actually, PAC is directly dosed into aeration tank. Consequently, this is the combination of biodegradation and adsorption. Therefore, the removal efficiency of micropollutant is going to be increased considerably. The energy consumption of this technology was 150 gigajoule per year, which is quite lower in comparison with those, the information technology. The carbon footprint of PACAS was 116 grams CO2 per cubic meter, which is quite higher in comparison with the information technology. The reason is PAC is considered fossil product. That's why it's quite high. But I would say there are some developments in order to replace renewable materials with PAC to reduce carbon footprint. If it happens, the carbon footprint of this technology is going to be decreased. And costs of the implementation of this technology was 0.05 euro per cubic meter and $0.059 per cubic meter, which is quite reasonable in comparison with those technologies. And the removal efficiency of micropollutant by PACAS, first of all, is a 60% when they use 10 milligram per liter PAC dosage, but when they increased the carbon dosage to 25 milligram per liter, they observed the removal efficiency increased by 75%, which is quite promising for this technology. But in terms of monitoring concept, so far one of the best monitoring concept is APC, Advanced Process Control, which is going to stabilize treatment process, is going to reduce energy consumption and costs. At the moment, I would like to invite Dr. Leo Carswell to elaborate on advanced process control. Thank you.
That's great. So good afternoon, everybody. Yes, so thank you for the introduction. So my name is Leo Carswell. So I'm going to talk for maybe about 15 minutes, a bit of an introduction to advanced process control. I'm going to cover maybe the different types of control, some of the technologies, some of the costs and some of the benefits, and maybe a little bit of experience in the UK, because that's where my work really is. So, but in 15 minutes, it's going to be a bit of an overview rather than getting into any detail. So let me first. So I work for an organisation called the Water Research Centre in the UK, WRC. So I don't want to say very much about this organisation, but it has a very long history, and we've been working with the water sector for many years, well over 90 years. And I've done quite a lot of work on sensors and instrumentation is my background, but a lot of work in recent years on process control and wastewater process control and the use of sensors. So I'm going to talk about some of the experience that I have through UK projects. So maybe a good place to start is really talking about what advanced process control, or APC, really is. So in terms of a term, it's really just a broad term for use of technologies and techniques for optimizing a process or a control system. So really moving beyond a very basic control system to a more advanced system. And in terms of the concept we're talking about here today, we're talking about wastewater treatment. So I'm going to focus in on the activated sludge process, which is the process which has had most APC applied. Really, this is the main part of the treatment process, the most energy intensive part of the treatment process, where energy APC is often used. And APC is used in that part of the process to control the dissolved oxygen level, the amount of aeration. So optimize the aeration to to perform the treatment process as best as possible. So where you may previously have had a set point, maybe a 2 milligram, 1.5 milligram per litre dissolved oxygen set point, rather than just have a simple feedback control loop set at a single point. Advanced process control allows you to do an awful lot more, and as was said earlier, optimize your process a lot better. So this diagram, I mention in here 3 of the APC approaches which relate to activated sludge. So, and I'll go through these a bit more with some examples a bit later. But the first box in the top in the middle is the use of a combined conventional sort of feed forward and feedback control approach. So, taking feed forward data and feedback data to optimize your process. And one of the systems that does that is the HACK real-time control system. So talk about that in a bit. The second one is a predictive model. So this is a learning predictive type model, what you might term a black box type approach. And I'll talk a bit about Perceptive Engineering. They're a UK company who have developed this technology for wastewater treatment based approach, and there's several systems that use that type of approach. So I will talk about some of those examples in a bit, but first of all, I wanted to cover how is advanced process control used, because there are some clear distinctions, and I know about how it's used in the UK, so I'll talk a little bit about that. But as was said earlier, it's all about reducing variability and getting better control of your process. And obviously, wastewater treatment process, you can't control what comes into your treatment plants, so you have a variable product. So getting any more control on it is an important aspect. In the UK, the current use is much about saving energy, saving carbon, saving cost, with managing the risk of variability as part of that. And it's about maintaining the effluent quality. So that's how it's used at the minute. It's very much about saving energy. So that's the red boxes at the top. The blue boxes at the bottom are the potential ways that you could use APC, but it's not used this way at the moment, at least not in the UK. So that's about additional energy savings through optimizing your process so that you can work much closer to your environmental permit limits. So essentially reduce any safety margin or headroom that you might have in the process. And that's not actually done at the minute, and there's several reasons for that, but and I'll mention them a little bit later. So energy savings is really the driver for a lot of activated sludge control, and that's because aeration is an expensive process. The aerators, there's a lot of money, electricity spent producing that aeration. So this is the primary reason why people are doing activated sludge process control. So these figures, they're not that up to date, and I'm sure that we will see some more recent figures in the work presented in a minute. But this is some model data that WRC did a few years ago. So you can see here that actually the second line down in the table is really saying that just updating your control system, so without doing any advanced control, there is the potential to save maybe up to 13% of your electricity cost for aeration. So that's really just demonstrating that a lot of systems aren't very well set up initially. If you do some advanced control, advanced process control, you can be expected to achieve at least a 15% saving through that. And then if you use the advanced control and work closer to your limits, you can achieve 20% plus. And I'll talk a bit about what the reality is in the field in terms of what people have been able to achieve. But they're the sorts of savings that you might expect. Although, as was said earlier, and really a lot of the whole point of this today's talk is that each site is different. So really, it's very site specific, and it depends on the conditions and the site that you're dealing with. So that's a bit about energy saving. The other aspect is really all about effluent quality. So how does that treatment, that advanced control of the treatment process affect effluent quality? And this is a graphical display, really a diagram which shows effluent quality. We've got 3 different time series data on here. So the green one shows typical effluent over time. It's varying, it's quite variable over time. The red trace shows how you might use advanced process control, and it essentially reduces the variability of those data. So less peaks and less troughs, more controllable, more managed, but essentially it's following the same level. Now, the blue trace is that third area which I talked about earlier, which is really because you're able to control the process better, you can essentially work closer to your permit limit. So you might be discharging at a higher concentration more consistently, but because it's better controlled, you're not going to breach your consent. So you might have a discharge limit of maybe 5 or 6 on that graph, and you're not going to exceed that because you're better controlling your process. You can look at this in a different way. You can look at this in terms of the distribution of the effluent quality from that plant, and this is where it becomes a bit more interesting. So the typical distribution of effluent quality from an activated sludge plant or wastewater treatment plants will have a long tail. So you'll have very few high concentration events. Your highest probabilities will be towards the low concentration. And that's the green plot. The red plot shows the activated sludge advanced process control process, really tightening that distribution, controlling that distribution. So around the mean, it's very tight around the mean, and the process is very well controlled. The future potential, the blue graph, is really just moving that to the right and saying you could operate your plant at a discharge more material to the environment, save energy, save carbon. But the reason that people aren't doing that, at least in the UK, is because that would mean more polluting load into the receiving waters. So the environmental regulator would probably say, sure, you're saving carbon through less energy, but you are polluting the receiving water more on an annual basis. So there's a balance between the about a few of the different some of the technologies. This is my area of sort of interest a little bit more, and I'm not going to go into any detail specifically for activated sludge plants. So HAC are very well known for making sensors and instrumentation. They've added to that technology a process control system, which is, as I said before, it's based on this International Water Association pollution research and control model. So an established model that's built into their algorithms, and it's based on feed forward and feedback control using DO, ammonia, nitrates, organic loads type sensors. So it's very well characterized. They've demonstrated savings of quite significant savings. I think some of the literature talks about up to 30% savings over a range of different applications. And at least in the UK, this is, I think, that some of the largest wastewater activated sludge plants in the UK are running this system. So it's well used and well known and well characterized. The photographs are actually just HAC dissolved oxygen sensors. That is not actually the control system, but actually I'm not sure you can actually tell, because the control bit is just essentially just software and electronics. The next system is a little bit different. So this is by a company called Perceptive Engineering. So Perceptive Engineering are not a sensor manufacturer. They're actually a company based in the north of England, which actually is, the background is all about statistical process control, model predictive control, data visualization. And they've done a lot of work on environments, manufacturing environments where you optimize the process. Maybe this is a bit different, where you have a known product coming in and you want to produce a known product going out. Wastewater treatment is a little bit different, but they've been applying some of their technologies, and their technologies are all around using a predictive model. So it measures what's happening on the site, the inputs, and measures the outputs, and it learns over time the relationship between the inputs and the outputs. So it's quite good when you've got a variable input and you might have different events, storm events, when equipment breaks, etc., etc. So this has been used on several sites. Some really good benefits achieved. In the UK, it's been accepted and used by several utilities. It is seen as this black box technology, so you don't really know what's happening inside the algorithm, inside the computer system that's operating it. So unlike the other processes where you can delve down into you can relate the algorithms to the fundamental wastewater treatment process, this is very much looking at a predictive model based on learning and relationships. So it's a little bit different, and that is seen as a challenge for some companies who want to know what's happening. The third approach is based on more empirical rule-based sort of systems. So I've put an example of a different type of monitoring here. This is a monitor that's from a company in Scotland, and it's an example of a wastewater activated sludge monitor that measures all sorts of things. It really monitors almost everything you might want to measure in a wastewater activated sludge basin. But this is the sort of instrumentation that you would put into the outputs from this type of instrument. And this is actually quite a popular approach with some companies who really want to understand the control approach that they're using. So they want to be able to develop the control approach themselves. So this has been used at least in quite a few sites in Scotland. I think it has been used around the world as well. It's quite a powerful monitor, interesting technology. So talk a little bit about costs. Now, these are a little bit out of date, these costs. They're all in UK pounds as well. But this gives you an idea of, as the size of the plant increases, the control system cost obviously increases. The amount of instrumentation you need also increases. But the key point I really wanted to make here is that the maintenance cost on this type of technology is not insignificant. So, and maintenance is required to keep the technology operating. So we're talking about putting sensors into a really dirty environment. So keeping them clean is important. So that's good. And then my final slide, I just really wanted to touch a little bit on some of the UK experience. So and I think I said at the beginning, the use of APC has really been driven in the UK, at least, by energy and optimization teams with targets within the water utilities to reduce their energy consumption, their carbon use as well. So it's been driven by them rather than for compliance or discharge or permitting reasons. So that's what the drive has really been, and that's been over the last 10 or so years. There have been some really significant benefits that have been achieved as a result of this technology. One of the messages that you hear from the water utilities in the UK is that they often achieve the benefits within the first year or 2 years, and they had very good benefits. The challenge was to maintain those savings, so trying to get the system to be optimized over the long period can be a challenge because of the maintenance required and because the technology needs to be continually looked after. It's not a fit and forget technology. These systems require accurate sensor measurements to be able to perform long term. And I think the UK, all of the UK water companies have got these systems in place, and I think they will all invest in them more, and we'll see them being used at more sites, probably more smaller sites as well, because they tend to be focused on the largest sites at the moment. But we will see more on conventional activated sludge plants. We'll see more involved in things like pea removal and sludge management as well. That will definitely happen over the next 5 or so years. And probably the final point I just really wanted to make was, within this wastewater environment, although you have people coming in optimizing processes for energy saving, really the compliance with the discharge permits, so the meeting that environmental regulation is a top priority. We have a phrase that compliance is king, so that's really always stands top of the list. So there's sometimes a bit of conflict between saving energy and maintaining compliance, but that is really the reason why you could achieve more benefits with APC. You could work closer to the permit limit, but it's not done at the minute because the compliance is seen as being absolutely important. The fines are very large, and actually any energy savings could be wiped out as a result of the large fines that might be imposed if you do breach your consents. So that's me. That was a very quick look at some advanced process control. There is obviously a lot more you can say about this, and I think a lot more that will be said about this within the project that's being presented, or the work that's being presented today. But hopefully that was a useful introduction and sort of sets the scene a little bit to help the later presentation. I'm very happy to answer any questions if we have enough time.
Thanks to Dr. Leo Carswell for his nice presentation. Actually, we have received some questions that I would like to ask. The first question, what was the total cost of the implementation of APC in UK? Is it possible to express the cost per cubic meter?
I think it probably is possible to put it as a cost per cubic meter. I don't have that information to hand, but I think that has been calculated, and it could be reported. I would say that there will be a variation between different types of plant. One of the key things that actually impacts the cost variation, or has impacted the cost variation in the UK, is whether the existing instrumentation is fit for purpose or is suitable for the APC. So the APC, the control mechanism, has a certain cost, but if you need to put in completely new dissolved oxygen sensors, ammonia monitors, and a COD monitor, then the costs can get much larger. So it can be quite variable.
Okay, thank you for your answer. And the second question is, the question is regarding the strategy. If you want to go for the strategy of 95 percentile, could you tell us a bit about the risk if you want to go for this strategy?
I think the work that I was involved with, and where these graphs come from, was really looking at that risk. And I think the actual risks, I don't think anybody has in the UK, at least, has applied this approach to actually look at to really, in practical terms, understand what the risks really are, because everyone is worried about going beyond the permit limit. The risk is that your plant, if the control approach does not work, if you have any problems at all, you'll be very quickly discharging beyond your ammonia limit or your BOD limit or your suspended solids limit. So you will breach your discharge consent very, very quickly, and there will be fines associated with that. So that is the risk. I don't think people have actually implemented this approach to be able to, in real terms, understand the potential. But definitely, when you look at those graphs, you can see that unless the APC is working, you have quite a major risk. So hopefully that answers the question. There's still a lot more learning to do, I think, in this area.
Okay, thank you very much for your answers, and questions are finished, almost finished. And thank you for your nice contribution to the webinar. Thank you.
No, thank you very much. I'm looking forward to the second part.
Okay, thank you, Dr. Leo Carswell. I'm back again. At the moment, we're done with the block A and block B, the input and also waves database. There are input for our model. So at the moment, I'm going to concentrate on block C, which is the outcome of the calculation of what-if model. What-if is going to calculate the impact of wastewater technologies, treatment technologies, and monitoring concepts in terms of costs, the water quality, and carbon footprint. The costs, I'm going to talk about CAPEX and OPEX costs and the benefit, and also return on investment, ROI. For water quality, I'm going to talk about water quality improvement quantification method. That Wat-IF is going to calculate the water quality improvement in a numerical way by two strategies, water quality index and Simone, which I'm going to elaborate on them. And lastly, carbon footprint. Wat-IF utilizes IFMA database and SIF software, which I will explain about both of them. Firstly, I start with costs. Actually, there are OPEX and CAPEX costs, operating and investment costs. These information are available in the reports of the implemented treatment technologies or monitoring concepts. But water managers need to know how much they are going to save, how much money will be saved. That's why Wat-IF is going to illustrate costs, cost of the implemented technologies and monitoring concept and figure. So it's quite easy for water managers. At the end, they can look at the figure and they can compare the cost of the implemented technologies and monitoring concept. And also, Wat-IF is going to calculate rest on ROI, rest on investment for water manager, which is very important because water managers need to know how long it takes that their investment is going to be recovered. I put an example in terms of the implementation of APC. As you can see, the investment was $165,000, but APC stabilized effluent quality, so energy consumption was saved by 20%, and that's why $240,000 per year was saved. So ROI was estimated 9 months. So it means after 9 months, their investments is going to be recovered. So this is the philosophy between benefit and costs that Wat-IF is going to help to water manager, and water managers can find out whether it is worth to implement a specific technology or a monitoring concept or not. In terms of water quality improvement, Wat-IF utilizes two strategies. First one is water quality index. This strategy is used for macropollutants, nitrogen, phosphorus, COD, BOD, and etc. If I want to clarify more about water quality index, I would like to compare this strategy with Dow Jones stock market index because the majority of people are familiar with this stock market index. For example, in stock market index Dow Jones, you see trends, whether trends are going up or whether trends are going down. This stock market index doesn't tell you anything about detail of companies, or for example, how companies are performing financially. So the only thing that you see just trends, whether they are going up or down. This is the exact way that water quality index works. Water quality index is going to show you whether the trend of your water quality water quality in effluent is going up or down. I put the formula for water quality index, as you can see in the slide, the right side of the slide. And Wat-IF is going to use this to calculate water quality index. We use water quality index for macropollutants because it's possible to measure individual parameters in influent and effluent. The second strategy is Simone Smart Integrated Monitoring. It is used for micropollutants, pesticides, pharmaceuticals, etc., which is a novel bioanalytical strategy. We use, or I would say, Wat-IF utilizes this strategy for micropollutant because it's impossible and it's very, very expensive. It costs a lot of time, it costs a lot of money if you want to measure individual parameters in terms of micropollutants. Simone is going to show you the effect of the group of substances, the group of pesticides, pharmaceutical in your influent. This is effect-based and measure for ecotoxicity. The Simone strategy is two-tiered. Tier 1 is bioanalytical, hazard identification of effluent at your site, at your water utility. And tier 2 is ecological risk assessment. And as you can see, this is the formula of Simone score, which our model is going to use it to calculate Simone score. So if Simone score is more than 1, as you can see on the right side of the picture in red score, if it is more than 1, so there is a potential risk. So tier 2 should be calculated. But if Simone is less than 1, there is a low risk, so it is not necessary to calculate tier 2. This graph, this is the implementation of Simone. Actually, this is about the implementation of PACAS technology in one of the wastewater treatment plants in the Netherlands that Simone was used to assess or evaluate water quality of effluent. To be honest, this strategy is quite complex. The more I explain, the more people might get confused. Therefore, I put the reference at the bottom of the slide. If you need more information or if you are interested in this strategy, you can check the reference, or you can check the link that I put in the bottom of the slide, or you can send me an email. I'm going to elaborate on this strategy very well. And lastly, carbon footprint, IDAMAT database, and climate impact forecast. This is IDAMAT database. IDAMAT is Industrial Design and Engineering Materials database based on life cycle inventory. This database was built by Delft University of Technology in the Netherlands. It was built based on tons of literature review, interview, and many research. This is quite huge database containing carbon footprint of different materials, substances, as you can see, for example, for chemicals, organic, inorganic materials. As I highlighted in yellow, you can see hydrogen peroxide, and in the right side of the picture in circle, in red circle, you can see the carbon footprint equivalent for hydrogen peroxide. But it's quite difficult to use this IDAMAT database, because this is very big database. Our model utilizes climate impact forecast software. This is a software, as you can see the picture of this software in my slide. There are some questions and there are some blocks that need to be filled out. For example, you need to put information about your process, about your product, process, your material and type of energy that you are using. And at the end, if you can see, this software is going to calculate the carbon footprint of your process or anything else. And it is going to calculate the equivalent to, for example, 596 times driving car, or 4,860 passengers flying, and etc. But if you need more information, or if you are interested in this software, you can check the link that I put in this slide, or again, you can contact me. You can send me an email. I'm going to elaborate on this software for you. At the moment, we are done with all required components for Wat-IF model, all blocks which are necessary to run and to get the outcome of the model. So now we are going to see the outcome, the final outcome of the model. The outcome of the calculation of the Wat-IF model is going to be illustrated in the graph such this that I put in this slide. As you can see, there are information regarding costs in blue square, carbon footprint in red, and water quality in green. So at the end, Wat-IF calculates the impact of implemented technology in terms of cost, carbon footprint, and water quality in figure. So it is very, very easy for water manager just take a look at this graph and they can compare very easily. So these outcomes are numerically comparable. So water manager can take a look at this and to make a decision whether they want to use a specific technology or monitoring concept or not. So for conclusion and at the end, I would say your costs undoubtedly are going to be reduced because water managers don't have to pay water experts or consultancy companies. Just they need to click on Wat-IF, and Wat-IF is going to calculate the outcome and graph so they can make a decision. And also water quality will be improved because you are aware of the status of your water quality and you can take right action to do for your water quality in effluent. And also carbon footprint, you will be aware of a carbon footprint and energy consumption of implemented technology or monitoring concept. Here is the end of my presentation. Thank you for your attention. If you have any question, please ask. And I would like to invite Dr. Corona Carpenter to join me to go through the questions.
Okay, go ahead.
Yeah, the first question is, this tool was built using data of Dutch wastewater treatment plants. Can it be converted to be implemented in other countries as well? Yeah, I would say it is possible to convert this model to any other version to be implemented in other countries because we use WAVES database, which is a huge database. It is specified for wastewater treatment plants in the Netherlands. So the only thing that we're going to need just a database for some information, realistic information, and realistic data in terms of wastewater management to build the default settings for a specific model if we want to use it for another country or another purpose. That's just the only thing that we need is default setting. We need to change the default setting because the default setting which we determined is based on wastewater treatment plants in the Netherlands.
Yeah, I'd like to add something to that. I think that in many cases there will be some parts at least of the wastewater treatment system that will be very similar to how we do things in the Netherlands, where, I mean, in that sense, we're not unique. A lot of wastewater treatment plants all over the world will, for example, use a biological treatment step. So we can use that information that can be converted, but I agree with you that we need specific data from other plants to see how they perform, to make sure that whatever we put in the model is indeed meaningful and based on realistic data. Yes.
Thank you. And the second question is, how does this model help to reduce the effort of water managers while reducing costs at wastewater treatment plants? Obviously, water managers don't have to do anything. They don't have to do study or research because we have already carried that research. We analyze technologies and everything. The only thing that a water manager is going to do just click on the model, and at the end they are going to get required information in terms of the implementation of technologies or monitoring concept. And for costs, as I mentioned, they don't have to pay anything to experts, water expert or consultancy. because Wat-IF is going to help them very well.
Sounds very good to me.
Okay. And
I think there are a few more.
yes, you mentioned by increasing PAC dosage removal efficiency increased. It means more PAC dosage removal, more PAC dosage, increase removal efficiency. Yeah, actually, I had an interview with one of the experts involved in the implementation of PACs in one of Dutch wastewater treatment plants. She told me when they increased PAC dosage to 25 milligram per liter, removal efficiency increased to 75. But after that, when they increased the PAC dosage, it didn't change so much. But she told me it is possible maximum you reach the removal efficiency to 80%, but after that it doesn't matter. It didn't change actually at wastewater treatment plants. Yeah.
Yeah, I agree. With an increase of the dose, it increases the removal of the micropollutants, but only up to a certain point. And after that, you can add a lot more, but it just will not do anything extra. It's exactly that. Yeah.
Okay. Thank you. And the question is it possible for users to add technologies themselves into the model to calculate the outcome of them? I would say we have already incorporated technologies. We analyzed them. We studied about those technology, and we have already incorporated those technology and monitoring concept into the model. So users don't have to do that. They need to click on the model. I would say we are in the initial phase of the model. So actually this model is designed to, for example, more technologies and more monitoring concepts will be added. But at the moment, no, we have one treatment technologies and one monitoring concepts. But no, users cannot add their own technology because we have already done that.
Well, the thing is, by adding a new technology, of course, you have to take into account how does that fit into the calculation of the carbon footprint, what exactly do we know about the costs, and can it be converted to the information that is put in about the wastewater treatment plant? Is it related to a specific treatment step? What we do encourage the users to do is to suggest technologies to be included, but the actual inclusion will be done by us. And but of course, suggestions are always very welcome.
Okay. And questions. How have you used the information on the WAVES database to determine the default settings for the model? I would say we collect the required information in terms of main characteristic of wastewater treatment plants in the Netherlands from WAVES, and we use a descriptive analysis method. For example, we made a histogram, and we considered the distribution pattern. The distribution pattern of data, if there was quite symmetrical, we use mean, and if there was not, for example, there were high or low value, we used the median to determine the default values.
Great.
And the last question is, what type of models are being used to evaluate the performance of different technologies? Would you like to answer? What type of models are being used to evaluate the performance of different technologies?
The technologies that we evaluate that are included in the model are based on pilot tests that have been performed in real life. So we use detailed information from those pilot test reports. It's usually reports that have been written about a specific technology that has been implemented at a specific wastewater treatment plant. And we use that information in the Wat-IF tool to convert the data collected to make it applicable for a wider range of wastewater treatment plants. And that is all based on those characteristics that you discussed, the water quality characteristics, but also the volume of water treatment, the actual wastewater treatment steps in place at a wastewater treatment. And we just pick the whole pilot test apart and include what information we have into the tool. So it's not directly based on other modeling tools for treatment, but it's the model uses actual data from pilot tests.
Okay, thank you. And we have a nice comment from Ron van der Olst, the expert of Simone, the author of Simone. So if you need more information than you have, you need more question, you have more questions, you can contact his email, as you can see in the bottom of this bar. Okay, at the moment we're done with the question. Questions are almost finished, and this is the end of our webinar. Thank you for your attention.
Thank you very much, Roozbeh, and thanks again, Leo, for doing the presentation. Thank you all for attending. We will, as you have noticed, we have recorded this webinar as well. So the recording of this webinar will become available through the Sensilo platform, and you will receive an email when the recording is available for you. So for now, I wish you, on behalf of all the team of Sensilo over here, a very nice day, and we hope to welcome you at one of our events in the future too.
Thank you.
Goodbye.
Goodbye.